I'm Jeff Yarger. I'm a professor of chemistry, biochemistry, and physics at Arizona State University. I'm making this video today to introduce a series of lecture notes that I've made on general thermodynamics, and more specifically how this can be, the salient points that are used in biological thermodynamics, some of the key features. So in past videos I've covered, it's a series of 5 or 6 parts. I've covered the first 2 sets, and today we want to just briefly look at set number 3 and some of the primary topics that are covered in this set. So I provided this at biopchem.education. They're downloadable in PDF format. And I've included a cover page that covers kind of the topics that are covered in each one of the sets. So in set number 3, a lot of it starts with, from set number 2, where we focus was on entropy. It continues some of that through the first half, looking at some of the Maxwell relations for entropy, Gibbs-Duhem, etc. And then it moves on to really looking at the relationship to chemical work, which I would say is really at the heart of chemistry, looking at chemical potential. And oftentimes, anytime we look at chemical potential, this is synonymous with looking at molar Gibbs free energy. So I'm not going to go through exhaustively here. I want to point out a couple key features of this. And really where I'm going to focus is that on some of the Maxwell relations and introduction to some chemical potential. The other thing I will say, which is when we say this is about general thermodynamics, really what we're saying is that this is equilibrium thermodynamics, and really some of the critical concepts to understanding that is this idea of, you hear a lot that reversible processes maximize work, that you're maximizing the amount of entropy in a system, you're minimizing the energies in certain system, etc. And this really first part talks about what you're doing when you're looking at thermal equilibrium and mechanical equilibrium and chemical equilibrium, etc. And what functions or what different types of energy, etc., is being minimized or maximized in these types of processes. So I think that's oftentimes really critical to understanding kind of the molecular nature of thermodynamics. So I would strongly recommend you look at some of that. What I want to jump to is quickly, looking at right here some of the Maxwell. So when we generally introduce mathematics of thermodynamics, talking about partial derivatives and the idea that these partials that we look at, we're almost always looking at multivariable, which is why we look at partial derivatives. And we're usually looking at state functions, things that have exact differentiation associated with them. And this leads to Maxwell relation, or a linkage of the cross or mixed partial derivatives associated with it. And we've introduced several in the past, and we introduce several more when we get to looking at Gibbs free energy and molar entropy, and how it really relates to, oftentimes when we start thermodynamics, we in a sense start off with multivariable too, but we do just that. We start, for example, with the Gibbs free energy talking about just temperature and pressure. In other words, we say it's a closed system so that the change in the number of moles is 0. And we do that because then it's just 2 variables, not more to have to keep track of. At this stage is when we're going to get to really the biochemistry or chemical part of thermodynamics, which is really defined by reactions. Chemistry is the change in stuff. The change in chemistry or chemicals or number of moles of different components in a system, right? So now we're going to really, in the notes, bring back a third variable and look at that much more extensively, or we're really going to start talking about, as I would put it, the chemical work component of this. And so this is really where this starts, and it starts back with our basic math of this, that this also comes in as an exact differential, and so we look at that. And then we start using that to really define some of our chemical potential. And one of the critical things that, Gibbs-Duhem relation, et cetera, which really plays a critical role when you're looking at chemical equilibrium, et cetera. So I really hope that this set of lecture notes that I produced, which really goes through step by step without skipping any components on these. So it stays to just the basics and doesn't give a lot of detailed examples, and I'll do that separately. This is really meant to just focus on the key fundamental concepts and really showing those from an intuition and a complete level, looking at the math, etc. Thank you.